My name is Ken Bedwell. I'm one of the founders of a company called Anomaly. Right now it's 2.5 guys in a garage. We got a booth in there, so come check us out. We're building products to simplify the cloud. We've got a basically GUI for the cloud. If you want the spiel, I'll give it to you, but there's a lot of anomaly detection in here, which I'll get to in a minute. Just trying to make the cloud easier, and come on by for a t-shirt. Running out of small t-shirts, but if you wash it 3 times, it should be good to go. Some big stuff that I've worked on. AT&T, I worked on something called the Kings Mountain Hadoop cluster. 6 petabytes, 500 some odd machines. It's a big deal. Stored telephone numbers, and there were anomalies, and we detected them because that's the point of the talk. Bank of America did all the Cassandra at the bank. There's 1,000 servers, 3 FTEs. Worked on the fraud system. There were deviations. We detected them. Cisco, they had 22 data centers in a big European cloud, and all of the data, telemetry data from all the instances and boxes and all that kind of stuff flowed into a couple central points in Europe, and we had to detect outliers, people breaking into stuff, billing problems, things breaking. And finally at IBM, we did exabyte scale data encryption, and in those clusters there were irregularities that needed to be detected as well. There's always stuff outside of the normal. The year was 1984. I had a lifelong obsession with anomalies. I don't like things that are, it's not OCD, but I don't like things that are kind of off kilter. So that was kind of the first thing I noticed. Second thing I noticed in the 3rd grade, I was about 5'3". I was taller than my teacher. So I knew something was up then. This is an actual photo from 3rd grade. That's also a bar graph if you look at it. So we'll get to it in a minute. This is noise. This is an anomaly. Talk about that in a minute. So true story, the 5'3" bit and the teacher, that's not actually me. Let's fast forward, it's 1998. There's some of my jams, especially these guys. Big fan of Destiny's Child, as you can tell. And I had moved to Oak Ridge, Tennessee, working in the nuclear industry. And one of the things that we worked on is called low background spectrum identification. So a place like Savannah River Nuclear Plant, they would wash all kinds of laundry. They'd put samples in the hopper. They'd go run through, detect some nuke. They know where it came from. They could actually identify it and know whether or not somebody was getting sick. If there was some here, they'd move it over to here. Analyze it further. If they really want to know, they'd take the one that was broken and stick it in this thing and leave it there for 3 days. It's an example of pipelining that we're going to get to in a minute. So that's what they're looking for. They're looking for different types of isotopes. If you got this, you probably smoke a lot. If you got this, then you're in Chernobyl. Bad things. That's what they're looking for. These are anomalies. Typically, you were to measure me right now, everything's along the bottom. If you got any of this other stuff, you got problems. So what's the plan? What we're going to talk about? What's an anomaly? Should be obvious, but it's a little more nuanced than that, obviously. Got some use cases. So different stuff in our industry that you'd use this kind of stuff for. A little bit of light math, that's all I'm capable of. A little bit of Python, a little better at that. We'll talk about scaling at the end, we'll bring it all together and talk about how we do it at Anomaly, because that's the most intimately familiar use case I've got right now, and it kind of ties it all together, scaling, the Python, the math, and some of the use cases. So what's an anomaly? My brother-in-law. Things that are different from normal. Things that are outside the norm. That's the bell curve, and we'll talk about that in a minute. Essentially things that are not expected. So there's also things that are confusing the situation. There's noise, which is these points, and there's anomalies, which are easy to identify because they have big red circles around them. But it's not that typical. It's not that simple when you actually do things at scale. So we have to figure out the difference between the two, and the difference between the two is up to you to decide. Anomalies exist in context. All data exists in context. And there's time context. So 90 degrees Fahrenheit is not an outlier, especially in Florida, unless it's winter. Then that's strange. And then in space, it's not an outlier unless you're in Alaska, because that doesn't typically happen. It's not newsworthy unless one of those two things, it's outside of the normal one of those two things. So you got to take everyday piece of data you have and think about it in terms of context. So there's seasonality, time, space, where it's happening, when it's happening. All those things need to be considered as you figure out whether or not a data point is actually a problem or not. And context is important. So I don't know how they measured temperature 1,000 years ago. I guess they pulled ice cores or something. But this is some data from the government about global warming. I'm not going to tell you it exists or not. I believe it does. But I'm not going to tell you. I'm going to pick your politics for you. So essentially, they measured the median temperature somehow over the last 1,000 years. And it looks like it's getting a little bit warmer. And I forgot to mention I'm also a fan of stock photos. So we're going to have some awesome stock photos in here. Appears to be getting hot. It's good to know. Please keep on all your clothes, in spite of what Nellie told us to do. Over the last 10 years, see the same thing. Variations all over the place, lots of noise, noisy data, not a big deal. That's why I don't freak out about that big point over there at the end, because there's a lot of variation in the noise. You look at it over a long enough time scale, and I don't know how they measured temperature 100,000, a million years ago. They did. If this is us right here, over a long enough time scale, our current rise does not seem to be that out of scale. So again, data in context. How big of a time scale are you looking at? Everything's kind of fractal. The more you stretch it out and evaluate your data, you get different answers. So you got to figure out which time scale you're looking at and what matters in that context as things change over time. So what do? You got to understand seasonality. This is seasonality. Things go up, things go down, things go up, things go down. The revert to mean, where are you in that seasonality cycle? Understand your noise characteristics. If you're dealing with sensor data and you have noisy sensor data coming in and you have data that's all over the map, is it all over the map in a tight range, in which that case that's okay, and that defines the high and low points of what you're looking at. If you're dealing with stock data and you can be assured that all the data points are correct, mostly, then you can determine what to do in cases of rapid and sometimes volatile changes. And do you need every data point? We're going to get to that in a minute. Do you need, if you're picking stocks, if you're detecting sensor data, do you need to keep every single data point? They have down to the millisecond stock data, but in order to determine whether or not I'm going to buy or sell Apple, I don't need all that. I need it at the end of every day. So some data you can throw out. It's too much data. It causes you problems. Document your assumptions so that 6 months from now you can understand what it is that made you determine whether or not it's a data point. Adjust as you go. And then don't overfit. And overfitting is you tune your model until it is exactly perfect for the space context and time context that you're in right now. And as your environment changes, as global warming moves along, as the stock market moves around, as cryptocurrency jumps up and down, suddenly your model doesn't work anymore because you tighten the parameters down too tight to not allow for change. Cause you problems. Use cases. Talk a little bit about this. Some of these I've worked in personally, and then some of them I haven't. Fraud detection, it's a big one. Favorite fraud detection story, I went to Costco. I got 5 kids, I must bought $1,000 worth of diapers or whatever I do. Go back out to the car, come back in line, had to buy something else. They wouldn't let me because my bank had determined that no sane person would go into Costco twice in 20 minutes. They had it tightened down too tight. They overfitted the model. So supply chain, some good use cases for that. So you're looking at variations in shipping, variations in pricing, variations in supply and demand of various goods and services. Supply chain is all about bringing together the right stuff at the right time, and if one thing is off, then the other thing is off, and the end result is off. So predicting the ebbs and flows of all that type of thing. Education, this is exceedingly controversial. So bell curving kids is a sport that we seem to do quite a bit, and a lot of money at stake. Teacher bonuses and all that kind of thing. But there's an ocean of data out there that gives them the ability to at least attempt to do that kind of stuff. And doing it right has proven to be hard, as we can all attest by where we are now. Healthcare, detecting various cancers. So I had some slides up here. The one that I showed was a cancer slide at some point. It was rolling through in the before I started talking. Automatically detecting anomalous conditions in the body that doctors can't always catch is important. I think we're going to get better and better at that. And there's a ton of work in this right now. IoT infrastructure, the last two I'm pretty familiar with. IoT infrastructure, so stuff measuring things and sending it back to the home base, determining when something's broken. And finance, I worked for a hedge fund for a while, worked at Bank of America. Data coming in, looking for weird stuff and reacting to it in different ways. So, confusion matrix. It is actually confusing. That's the best picture I could find. It's kind of abstract, but make it easy. So, if you're talking about actual values, what actually happened? Were you fraudulently trying to buy something from Costco? Were you not fraudulently trying to buy something from Costco? Did they predict, yes, you were trying to steal from the Bank of America at Costco? No, you weren't. If they say that I was stealing and I wasn't, that's called a false positive, type 1 error. The only consequence from that, I got to call the bank, I'm mad at them, they put it back on, I go and buy the last $1,000 worth of diapers. If, on the other hand, I was trying to steal from them and they predicted that I wasn't, type 2 error, that's significantly more problematic for the bank because they got to go try to get that money back so they got it wrong. Which is problematic and which one is not is, again, dependent upon context, whatever your use case is. So, it's not called talk on the beach, it's code on the beach. So at Anomaly, we use a couple libraries for this. One's called PyOD, that's outlier detection. And I'll put a screenshot of this up on Twitter or something. Or if you want to just come by after and I'll make sure you get the link. What that's good at is if you got a big CSV file, possibly more than 2 dimensions of data points, and you got them in the order you want, it doesn't have to be time order. You can throw it into that, get a couple of different algorithms to try, and it'll churn out some answers and tell you where outliers are. We'll do a little demo of that, a couple of different ones. Datastream.io, I don't know who these guys are, but they got a bunch of stars on GitHub, and we actually use this as, they have a couple of outlier detection algorithms that are pretty simple. And for what I need to combine some of those together, so I've customized this quite a bit. But ultimately, this thing runs streaming time series, and you can detect via windows, which we'll get into here in a minute, when things are outliers and when they're not. And then tuning that model, that's the sport. That's kind of where we're spend all of our time. So one of the algorithms we talk about, it's called angle-based outlier detection. So you go look at every point, you go look at its angles to some of the other points, figure out the cosine of that, store that with the point, and then figure out if it's very wide, like the angle between, if that's the center, the angle between that and that's very wide. All the angles in here are by and large, on average, very wide. That means you're in the center of a cluster. If they're very narrow, and the farther away you get, the more and more narrow it gets, then you're an outlier. So that's a lot of fun to write the code for that. Not doing it. Absolutely not going to do that. That's for the NLP logic guys to write that kind of thing way above my pay grade. So we use a library to take care of this because that's how we do it. And this is the PyOD stuff, basically instantiate angle-based outlier detection, hand it your training data. Now you got a model, you can persist this off. So you want to put this in a web service, you can. And then you run against real data. So you got your chunk of real data that you've sent to your web service or however you're running this. It gives you outlier flags. So for every data point, it's a 1 or 0. Is this thing an outlier or is it not? This thing, and then run it against the real data to get outlier scores. How much of an outlier is it? How far off is it? How much of something do we have to worry about here? All right. So, quick demo. We'll do it live. That's how we do it. Any Emacs folks in here?
Just you.
Shut up.
Can you zoom in a little bit?
Yeah, I guess I could. I'm not doing anything particularly interesting right now, but yes, I can. All right, so we're going to run the sample. And there's some extra code to it, but really that's all there is to it. So they take training set, which they know what the outliers are because you put together a training set. It's no fun in training if you have to make it guess. It's a whole different kind of machine learning. Again, it's out of my pay grade. And you run against a training set prediction stuff. So you basically take your training set, cut it in half, cut it into some percentage, sport to that as well, and then take that last bit and run it again, figure out where you are. Not 100%. It still thinks that these are part of the cluster for some reason. And then you take your test set, which is the real data in this case, figure out what it actually is, and then do the real prediction against this. Again, not perfect, it's pretty close. That perfection, that last little bit, is the decision whether or not you're going to overfit. Overfitting can be bad. You could get it to where this was perfect. You could do all kinds of fancy stuff to turn those guys green, and maybe this guy red because in later investigation you determine that he should have been red. But as your world changes, as you scale up, as the stock market moves, as cancer becomes more prevalent, as whatever it is that you're dealing with, your world's going to change, and your model's going to be overfit, and you're actually going to end up worse off than you are if you just kind of let it ride. How much to leave alone, that's part of the art as opposed to the science. Another algorithm, isolation forest. So this is not when you go alone in the woods, totally different. This is given a random partitioning of points. So you go through your data, you cut it up into different ways. You measure, this turns this into decision trees. You measure how far down the tree this goes, and then you apply a fitness function to it. And then the score of that fitness function determines whether or not, nope, not doing that one either. That's a lot of work, and we got libraries for that. Same guys, isolation forest. So it's going to look essentially the same. We're generating the exact same training data, so because it's a presentation, we want to look good. Same model. Make a model, fit it with some training data. Got some flags, 1 or 0, got some scores. How much of an outlier is it? And you can react accordingly. There's a lot of switches that you can tune in here. It's not as simple as this, but this is the gist of it. The defaults are pretty good. And the things that I'm running when I go over here and run these are the defaults. Isolation forest. This one comes highly recommended. As you can see, it is better. Got all of them right here. A couple of them wrong up there. But in essence, as I understand it, that one is, in a lot of the research, better for certain kinds of data. An interesting thing that I'm interested in is it scales better. It doesn't have to do essentially a Cartesian product of all the distances and all the angles between all the points. It randomly partitions stuff up. That's a fast operation that you can actually parallelize really easily. So you can turn this into a terabyte of this stuff, buy a giant Spark cluster, and get it done really quick and not have to actually calculate every single point, talking to every other single point all the time. Scalability is important, and that's one of the considerations we have to think about. How much data you have, how often you're going to be running it, how often does it change, and what are you going to do if it's really big? Really big, like bigger than the RAM of your machine. So time series anomaly detection. So data points are coming in. It could be the stock market, it could be servers, how much RAM is in your server, how much disk space, all that type of stuff. You want to keep a window of data ready to go to measure stuff. So as data comes in, t equals 1, 2, 3, move down the block, drop off the last one. Move down the block, drop off the last one. How big is that window should be? Completely determined on your context. How much RAM you got, what it is you're doing, what those numbers are, how accurate do you need them to be. Lots of considerations there. I always like to say experimentally determined in my project proposal, which means I don't know, but I'll figure it out. Check the incoming values against the data in the window, and there's various things you can do. If you've got a lot of data, you're going to want to do this as simply as possible because the data is not going to stop, and you're going to want to get the answers quickly. So this is the bell curve. It's also called Gaussian distribution. 68.2% is inside of one standard deviation. Outside of that, you got your 27 something percent outside of that, outside of that, outside of that. Where this falls in here is very easy to calculate, which I'll show in a minute. And if you fall in one of these ranges, if you say that you want only outliers to be out here or out there, conversely, then that's very easy math to do. Hold your window, do essentially, an average and some other division, which even I can handle, and you can determine if you got an outlier. Easy stuff. This is also a Gaussian distribution. It's Carl Friedrich Gauss. So we can see there's some outliers over there looking the wrong way over there. Good stuff. I was up late last night, guys. I'm gonna need a little more out of you. Some of the libraries that we use, Pandas. Pandas is it's pretty great. It's backed by C, which means it's fast, but that's all transparent. You throw arrays into it. You can do all kinds of fancy manipulations. It's as good as however much RAM you got. NumPy. If you say it NumPy, you're saying it wrong. We don't say Python, we say Python, so it's NumPy. Get it right. Scikit-learn. We don't actually use that, but I use it all over the place. So it's not in here. Doesn't mean we don't love it. We'll get you some. So what is this? This is, we have that other library, whose name is escaping me at the moment. This is a class that you can write to plug into this library, and it will feed you the streaming data and run this through. So the streaming data library that I've got, throw data at it, tell it which estimator, and it will fit this into the framework. So the first thing it'll do is it'll fit against the window. So you determine through some configuration how big a window you want. Starts building up the window, does the average, standard deviation, and how long is this effective sample size, which is the name of the window, fancy name for window. Probably should have just called it window to go with the rest of the talk. But the next thing is it updates as data comes in, and once it builds up a sufficient amount of window, then it starts scoring. And this is fitting it inside the Gaussian curve. Where are you in the bell curve? Out toward the edges, in the middle? This cumulative distribution function essentially says, what are the odds of this number fitting inside of that bell curve? We use that to score everything. And then flag it, just basically determine, is this guy above or below the threshold? And that can be two-sided. Is he outside? You take the absolute values outside the threshold on either end. If we only care about positive values, then we worry about stuff that's one-sided determination. All right, got a demo of that. So let's see. I need a tall guy table. I'm struggling here. Yeah, man. It's like flying a coach. It's terrible. So we're going to run some data I put together last night around car data. So it essentially models stepping on the gas and then acceleration in a car. I generated some data to look exactly like I wanted to. We're going to run the percentile, which is essentially the same thing as the Gaussian. It does percentages. It's a little bit faster. Very simple. And if this all works well, it didn't. Here we go. So this is going to generate some data. Data's flowing through. Give it a second. Car's starting up. And it's already detected some anomalies. So what this is this window goes all the way back to here, and it says these values are sufficiently low that we should tag them based on the data up here. No anomalies here. It's all flat. It's starting to get some data coming in and detect some anomalies. And now, because it's learned enough, it's starting to get something simple or sensible. So these are things you'd probably want to alert on if this was stock market, blood pressure, etc. What we see is there's a ton of red dots. So the tuning of this is probably saying, this is probably too loose. Like if this is pager duty, then you're waking up a lot at 2 in the morning if this is going off all the time. That means we got your screws too tight. So we need to go back in and adjust the metrics that we use, adjust the parameters of the system. And this tuning process is continuous. Picking the algorithm, that's step 1. Building the system to take all the data in is step 2, and kind of interchangeable with 1, because you may change the algorithm as you experiment. And then tuning this is going to take the rest of your life. Because as your world changes, the parameters are going to change. And if you don't want to be getting up at 2 in the morning, you got to take care of all these different anomalies and figure out what is an anomaly and what isn't. If it was really this tight, I would argue that none of these are anomalies. I need to have a longer window. I need to have a tighter threshold. I need to say, okay, it needs to be double this to wake me up at 2 in the morning. That's the type of adjustment I would make here. So this observation of what it is that you're actually getting out of the system, you're in beta, you just released the thing, what do you do with the data points that you got? When do you want to be paged at 2 in the morning? All that kind of stuff is the tuning of the system that you're going to have to do over time. Scaling. So that was fun. I just ran that in 2 megs of RAM on Python on my Barbie-sized laptop. You got a terabyte a day coming in, and one of the projects I had 3 terabytes a day of data coming in, and it never stopped. Then what are you going to do to actually process all this stuff? A couple different tricks. Parallelism, more cores. I'll take all your cores, all of them, all the time. If we can run lots of processes and orchestrate that in a way that doesn't fall over, and then when they're all done doing whatever math they're doing, it comes back on the other end, all that orchestration is hard. There's some stuff out there to help solve it. We'll talk about that in a minute. Sampling goes back to, do you need every value? The answer is probably no. But figuring out what you can get rid of, context dependent. Everything's about context. Know your data, know your assumptions. And then multi-pass pipelining. I'm a big fan of this, and we'll talk about that in detail here in a minute. So parallelism. Anybody use Spark? 1, awesome. So this is going to go well. Spark is Hadoop done right. Hadoop goes back 10 some odd years. Giant clusters of Linux boxes running Java processes that process things in parallel. Probably the second generation of web crawlers was all built in Hadoop. Doug Cutting, super ninja programmer, built all that stuff. There's layers on top of Hadoop now. Spark is one of them. It takes all the complexity of building Hadoop jobs and rolls it into something that's a lot more functional, a lot easier to deal with, and consumable. And nobody writes Hadoop raw anymore because Spark is so awesome. It's everything you need to chop up data, run it in parallel, run it in the cloud, run it wherever. Streaming or batch. I've not done a lot of streaming in Spark, but I know that you can do it. Batch mode is what I typically do. You throw a bunch of stuff up there, you run it through, get an answer out the other side, wait till tomorrow and run it again. The streaming that I have done has been for this giant multi-terabyte per day project. So learned a lot there, learned a lot of what not to do. And you write in Scala or Python. So obviously I'm going to pick Python if given the choice. Ironically, the streaming thing I did in Scala. So sampling. Do you really need all these data points? You can kind of blur your eyes and get the curve. You don't actually need to keep every single data point to know this stuff. If you've got all this data coming in, you need to make important decisions, life or death decisions, maybe you do need to keep every data point. But if you're trying to basically estimate when a tractor is going to go down so you know when to repair it in advance of the next day's work so you don't have any downtime, you probably don't need every single data point. You've got 1,000 tractors, but not a couple terabytes of data. You can save yourself some money in the cloud by not actually measuring every single data point. So that cost control, CTOs like that. So you're thinking about data, save a little money. Don't make that decision until you figure out what kind of numbers you're going to get when you bring everything in. Can you actually scale it back by sampling? Time series sampling, a different way to look at it. So for every period, for every time slice, there's an open and a close and a high and a low. That can all be condensed and turned sideways in what we call box plots. So you can condense that whole graph that we had into something a lot similar, a lot shorter, and easier to process, and just send that metadata through and make decisions based on that. So you can say, okay, the high for that period is outside of my outlier range. The low for that period is outside of my outlier range. I need to go back and investigate that period. This is what we call multi-pass sampling, or multi-pass, we'll talk about here in a minute. But picking the resolution is key to getting this right. There is a high, open, close, and low for every year of the stock market. If I made all of my financial decisions based off of that, I'd be missing a ton of moves inside the stock market. Also, there is a high, open, close, and low for every second of the day of the stock market. Warren Buffett doesn't look at that. He doesn't care. He doesn't care about all those micro moves because his style of investing doesn't look at every tick. So picking your resolution, the time period over which you compress this stuff is very important. Again, context. Context is literally everything. Multipass. So I talked before about nuclear physics stuff. Clearly I'm not a nuclear physicist. But they would run these very slow processes, kind of fast actually compared to the deeper dive stuff, but they'd run these processes through to figure out if there's any radiation in particular samples. And when they saw that, they would go and find samples from around there and run that through deeper dive. And there can be multiple steps of this. In the nuclear sample from before, there were about 4 steps of this. They got all the way to the end, and they would alert and react and go pick somebody up in an ambulance or hose them down like in Chernobyl or whatever it is they were going to do. They wouldn't do that until they'd taken all those deeper dives. They didn't react too quickly. They didn't process all the data with the slow, expensive techniques, but this allowed them to narrow it down, hone in on the actual answer, and then do whatever it is that they actually needed to do based on the results of that data. So I'm going to tie it all together now. This is what we're doing in Anomaly. And this is not a sales pitch, I promise. This is exactly what we're doing on the back end. So it ties into everything that we do. It's a very relevant use case. We're basically worried about telemetry data from customer clusters, customer Kubernetes clusters, their applications, data they send us, whatever. We do pipelining. So we have fast processes to look for problems and learn. Deeper dives, which feed back into the faster processes to learn better. And then reaction, which is we alert and do stuff about it. Preferably automating whatever it is you get waking up at 2 in the morning for. Everything's elastic. So we handle a lot of scale stuff by parallelizing, and then that feedback loop of reacting to time series data grows and shrinks the cluster. So if we have a cluster that is problematic and large during the day, it will expand to fit. If it's small at night, it will shrink back down. It doesn't stay huge all the time because that wastes money, wastes resources. So using this data to make decisions in real time for things that are simple is something we're trying to pull off all the time. Some of the infrastructure pieces, RabbitMQ, you can use Kafka, different queuing technologies. What that does is as data ebbs and flows and the size of it and the amount of it comes in and out, you can elastically store this data and then processors take it off of the queue and process it. And as you catch back up, the queue diminishes and it ebbs and flows and allows you to not have to have everything on in real time all the time. It allows you to kind of parallelize stuff, but at the same time, not scale your infrastructure to handle your peak all the time. You don't want to build your infrastructure in such a way that you have to be as expensive as your worst day all the time if you can avoid it. It's one of the pieces that allows us to do it. No rabbits were harmed in the building of these clusters. Elasticsearch, I'm a huge Elasticsearch nerd. It scales linearly, so I can throw servers at it. It bigifies itself. It's flipping amazing. You can do all kinds of time series stuff with it. There's Kibana, which sits in front of it. It has a fancy UI for graphing things, which I don't use. I'm an Emacs guy after all. And then Redis is for caching things. So if we have decisions, meta decisions about the entire pipelining process that we need later in the process, we store that in Redis, and then after an hour it goes away, it manages itself. It's basically a RAM database, which you have different data structures in there, do all kinds of fancy stuff. Tying it all together, we've got customer assets, they're producing data. We fast filter by doing very simple algorithms. They're combinations of some of the Gaussian stuff we were doing, some of the averaging stuff we're doing, very simple, very fast. Determining if we think we have a problem. If we think we have a problem, then we send down through RabbitMQ, and all these arrows are RabbitMQ. The deep dive guy wakes up and says, oh, something wrong again, problems. He goes and picks out from Elasticsearch the time series slice that he actually thinks he needs, does a deeper dive, compares it to other time series slices in other streams, like if there's a high CPU, I wonder if there's a bunch of RAM, I wonder if we're out of disk, I wonder if we haven't rebooted in 6 years, I wonder. It goes and does all these investigations, it might take a while, and then determines what to do next. And what determines what to do next is context. All depends on context. Wake a guy up, go do something automatically, do nothing because we just did something 30 seconds ago, escalate, reboot a server, whatever. Reacting to the context, reacting to the information we get in context, and doing whatever is possible to automate, everything else we kick up to a human. And the hope is that we can learn and reduce the amount of stuff that we're kicking to technicians, because I hate getting up at 2 in the morning. My whole life's goal is sleep through the night. That's all I got. I'll be up here for questions. I appreciate the time. Again, check out your sponsors. Want to hear more about Anomaly, come by and see me. Otherwise, enjoy the rest of your day. Thanks, guys.